Welcome to the Computer Vault podcast, where I discuss the history of computers, computing, and IT. I'm Aidan, and today we're embarking on a journey into the history of the IBM Model 650 computer, a machine whose technological innovations, design ingenuity, and historical impact continue to inspire and educate us to this day. This episode is specially designed for those who cherish the evolution of computer technology, and it will cover the development of the IBM Model 650, its unique design features, and the profound influence it had on the computing landscape. Along the way, I'll share some fascinating anecdotes, examine key lessons, and offer insights that bridge the gap between technical detail and historical narrative. Our story begins in the early 1950s, a time when computers were not the ubiquitous entities that fill modern homes, but rather ambitious projects developed to solve complex scientific and military problems. IBM, already renowned for its innovations, was on a mission to produce a machine that balanced computational power with operational versatility. This ambition was embodied in the IBM Model 650, a machine that not only represented a giant leap in technology, but also became an indispensable tool for advancing computer science as we know it. During its inception, the IBM Model 650 was a product of necessity and bold vision. At a time when electronic computing was still in its infancy, the Model 650 was designed to harness the emerging capabilities of magnetic drum memory. It was a remarkable machine for its time, marrying flexibility with raw computational potential. As we explore its story, we will see that the Model 650 was more than just hardware. It was a catalyst for change, sparking a revolution that impacted businesses, scientific research, and government operations alike. I remember reading an old interview with one of the engineers who worked on the Model 650. He recalled late nights huddled around clunky punch card machines where every line of code was written by hand and debugged under the dim glow of vacuum tube indicator lights. Those engineers didn't just build a machine, they crafted a bridge to the future. This snapshot into the lives of early computer engineers sets the stage for understanding the significance of the Model 650. It wasn't just about computing power, it was about the relentless human pursuit of innovation. Let's now delve into the development and design philosophy behind the IBM Model 650. The story of its creation is one of iterative ingenuity, a process of overcoming technological limitations with creative solutions. The early post-war era was marked by rapid technological progress. Computers were transitioning from room-sized behemoths to systems designed for more practical applications. IBM recognized that to remain a leader in computing, they had to push the envelope further. The Model 650 was designed as a cost-effective, mass-producible machine that could serve a range of computing needs. The use of magnetic drum memory, a technology that provided a relatively inexpensive alternative to the memory systems of the time, was a key design decision. While drum memory was slower and lower in capacity compared to later forms of storage, it represented a practical balance between cost and capability. The design decision was groundbreaking because it enabled more organizations to access computational power without the prohibitive costs associated with early computer systems. In essence, the Model 650 was democratizing advanced computing by making it more accessible to academic institutions, government agencies, and private businesses. The Model 650 was imbued with a host of design features that set it apart from its predecessors and contemporaries. Some of these features in detail is magnetic drum memory. At the core of the Model 650 was its magnetic drum memory, which provided a practical means of data storage during an era when solid-state memory was a distant dream. Although the drum's rotating nature meant that data access times could vary, innovative programming techniques were developed to mitigate these delays. The machine was built with a modular approach, allowing for the integration of new components and the expansion of its capabilities. This design philosophy permitted the 650 to be updated and adapted to evolving computational demands, a concept still revered in modern computing architecture. Built with reliability in mind, the 650 was designed to be operational over long periods with minimal downtime. IBM's emphasis on sturdy construction and ease of maintenance not only improved the machine's shelf life, but also set industry standards for future computer designs. And despite its complexity, IBM engineers strove to make the machine accessible to operators who are not necessarily computer experts. Through intuitive programming languages and the use of punch cards, the Model 650 allowed a broader audience to interact with and benefit from computing technology. One cannot overlook the interplay between mechanical ingenuity and emerging electronic technology that characterized the Model 650. This machine was not simply another computer. It was a carefully engineered system where every component was owned to deliver efficiency, durability, and versatility. Working on the Model 650 was like trying to harness a wild horse. Engineers knew every circuit, every gear, every line of punched card code had to fit perfectly into the grand design. It was a time of great uncertainty, but also infinite possibilities. The journey to creating the Model 650 was not without its challenges. One of the major hurdles was reconciling the limitations of magnetic drum memory with the need for speed and reliability. Early computers often encountered synchronization issues due to the rotational delay of the drum, a problem that required creative engineering solutions. The engineers at IBM tackled these challenges head on by developing sophisticated programming strategies to optimize data retrieval, ensuring that the time lag did not cripple computation. This blend of hardware limitations and software ingenuity is a testament to the collaborative spirit that fueled computer innovation in the 1950s. Moreover, the Model 650's modular design required a level of foresight rarely seen before. IBM's design team recognized that the future of computing would demand scalability and flexibility, and they built these traits directly into the machine's architecture. This decision would become one of the many lessons that computer scientists and historians continue to draw upon. Now that we have a solid understanding of the development and design features of the IBM Model 650, let's have a look at its historical impact. The 650 was not just a technical marvel, it was a pioneer that paved the way for a host of subsequent developments in the computing industry. The Model 650 played a critical role in demonstrating that computers could be used effectively beyond large government labs or military installations. It made its mark across various sectors, from academic research to industrial applications. Universities began to incorporate the machines into laboratories and classrooms, transforming it into an invaluable teaching tool for the next generation of computer scientists and engineers. In industry, businesses quickly recognized the utility of the Model 650 in managing complex data and streamlining operations. Its relatively accessible design lowered the barrier to entry for organizations that wanted to harness the power of computational analysis without investing in prohibitively expensive technology. In this sense, the Model 650 helped to democratize data processing, a legacy that reverberates in today's expansive application of computers in business analytics and the big data management. Beyond its hardware innovations, the Model 650 stimulated significant advancements in programming and software. Since the machine relied on punch cards for its operations, the era gave birth to pioneering programming languages designed to be both human readable and machine executable. Early programmers, often working in cramped and makeshift computer rooms, developed novel approaches to eliminate inefficiencies imposed by the drum memory's mechanical limitations. This nurturing of early programming techniques led to the birth of more intuitive coding practices. The 650 is often credited with indirectly influencing the development of assembly language programming by emphasizing the need for low-level control over the hardware. These lessons, in time, influenced more sophisticated languages and software design paradigms during the subsequent decades. The impact of the IBM Model 650 extended well beyond its practical applications. Its introduction marked a significant milestone in the evolution of computing technology, a key turning point that helped solidify the idea that computers could both be powerful and accessible. By bridging the gap between experimental research and everyday application, the Model 650 set the stage for the mass adoption of computer systems in a rapidly modernizing world. In the history of computing, the 650 stands as an emblem of transition from bulky, expensive systems handled by a select few to machines that could be integrated into various facets of society. Its impact can be seen in the subsequent generations of computers that continue to combine affordability with functionality, in part thanks to the pioneering decisions made during the development of this extraordinary machine. When I think of the IBM Model 650, I imagine it as the spark that lit the flame of the modern computing revolution. It was a machine that not only performed calculations, but also enabled a new way of thinking about data, logic, and problem solving. For many, it was the first tangible encounter with the idea that machines could think and assist humans in unprecedented ways. One of the most enriching aspects of studying historical computers like the IBM Model 650 is uncovering the timeless lessons they offer. We're going to highlight three key lessons derived from the innovations and historical relevance of this machine. Lesson 1: Innovation through necessity. The IBM Model 650 is a prime example of how constraints can fuel creativity. Faced with technological and economic limitations, IBM's engineers had to think outside of the box and develop alternatives that were both effective and affordable. The pivot to magnetic drum memory, a less costly yet sufficiently capable solution, demonstrates how innovation is often born from necessity. This lesson reminds us that constraints, rather than stifling creativity, can serve as a powerful catalyst for designing solutions that push the boundaries of what's possible. As we now understand, limitations can drive breakthrough ideas that ultimately redefine technology. The 650 teaches us that robust innovation often emerges not despite constraints, but precisely because of them, a lesson that continues to inspire modern engineers and developers alike. Lesson 2 is the importance of modular and scalable design. The Model 650's modular construction was ahead of its time. Its design allows for incremental improvements and adaptability, a quality that is critical in today's fast-evolving tech landscape. The success of the Model 650 underscored the value of building systems that can evolve with changing requirements. By incorporating modularity, the engineers at IBM ensured that the computer would remain relevant, adaptable, and capable of meeting diverse computing challenges. For modern designers, whether it's working on hardware or software, the lessons remain clear. Creating technology that can gracefully accommodate change is a cornerstone of long-term success. Flexibility is invaluable, and the Model 650's design philosophy continues to resonate with today's emphasis on scalable architectures and adaptive system design. Lesson 3: The role of human ingenuity in technological advancement. The IBM Model 650 also serves as a tribute to the human element behind technological progress. The machine's development required not just technical innovation, but also a tenacious spirit amongst the engineers, programmers, and technicians who brought it to life. Their ability to overcome practical challenges, from synchronizing mechanical components to drafting innovative programming solutions, underscores the critical role that human ingenuity plays in the advancement of technology. This lesson, perhaps the most enduring of all, is a reminder that behind every technological marvel lies the passion, creativity, and perseverance of individuals who dare to push the limits. The legacy of the Model 650 is not merely in its hardware specifications or performance metrics, but in the indomitable spirit of its creators, a spirit that continues to drive innovation in the digital age. In the days of early computing, we didn't have the luxury of modern debugging tools or high-level programming languages. We relied on our wits and the collaborative efforts of our teams. Working on the Model 650 was a lesson in perseverance. It taught us that no problem was insurmountable if we were willing to think deeply and work together. For those of you who relish technical details, We'll take a closer look at some of the key technical aspects and innovations of the IBM Model 650 that made it a marvel of its era. The magnetic drum and memory architecture. The pivotal element in the Model 650 design was its magnetic drum, as we've mentioned numerous times, a cylindrical drum coated with a ferromagnetic material. This drum served as the primary memory, storing data and instructions on its rotating surface. Although drum memory had inherent latency due to its mechanical rotation speed, clever programming tricks such as interleaving and scheduling instructions to execute during optimal rotational positions enabled efficient use of this resource. These techniques were, in many ways, precursors to the caching methods and memory management systems that are ubiquitous in today's computing platforms. Engineers had to consider both the physical rotation and the electromagnetic properties of the drum, balancing speed, reliability, and maintenance concerns. The trade-offs made during the design process continue to be a point of study for computer historians and engineers striving to understand the evolution of memory architectures. Input-output and data handling. Another standout feature was its handling of input-output or I/O operations. Relying heavily on punch cards, the machine's operators had to translate complex problems into a sequence of instructions that the hardware could understand. This process not only laid the groundwork for future automation in programming, but also underscored the importance of user interface design even in its nascent stages. The development of efficient I/O processors was crucial because it directly influenced the computer's overall performance. The 650's processes for handling data input, error checking, and communication between various hardware modules were groundbreaking at the time. They provided early insight into what would eventually evolve into comprehensive data management systems and interactive computing experiences. Finally, software innovations and programming paradigms. Programming the Model 650 was an art form in itself. With the reliance on punch cards as the primary means of programming, developers had to be meticulous in crafting instructions that the machine would execute flawlessly. Early programmers experimented with what we might now call low-level programming, a direct dialogue with a machine's operational code. Innovations during this era included the development of assembly language techniques and rudimentary compilers that could translate human-readable instructions into machine code. These early innovations were vital in bridging the gap between the theoretical concepts of early computer science and practical working systems. Furthermore, the experience of programming on the Model 650 underscored the importance of error handling, debugging methodologies, and systemic documentation. The lessons learned in these early programming sessions have echoed throughout the decades, influencing the evolution of modern programming languages and development environments. As we reflect on the history of the IBM Model 650, it's important to appreciate not only its achievements, but also its lasting relevance in today's technological world. Even though the hardware and processes of the Model 650 might seem archaic by modern standards, the philosophical and technical innovations it introduced continue to shape contemporary computing. For instance, modern computing systems still prioritize the principles of scalability, modular design, and efficient resource management, a direct inheritance from the pioneering work on machines like the Model 650. Many universities and historical societies honor the 650 as an educational tool, using it to illustrate the early challenges of computing and to inspire new generations of computer scientists and engineers. Today's engineers, though operating in an environment of microprocessors and cloud computing, can look back at the Model 650 and see a blueprint for creative problem solving. The machine's legacy reminds us that each technological era builds upon the innovations of its predecessors, and that lessons from the past are invaluable in tackling the problems of the future. The Model 650 taught us that progress is not a straight line, but a tapestry woven from experiments, failures, and triumphs. Its legacy lives on, not just in our machines, but in our approach to innovation and resilience. In And wrapping up today's deep dive into the IBM Model 650, we've journeyed through a fascinating era of computing history. We uncovered how the Model 650 was born out of both necessity and visionary thought, delved into its design innovations, and examined the profound historical impact it had by democratizing advanced computing and fostering new paradigms in programming. We also learned three key lessons from this pioneering machine: the power of innovation under constraints, the enduring importance of modular design, and the vital role of human ingenuity in technological advancement. These lessons are as relevant today as they were during the dawn of the computer age. Before I finish, let's just reflect on this incredible journey, a journey from the clanking, drum-powered halls of the IBM Model 650 to the instant, interconnected world of modern computing. It's a reminder of how far we've come and how the pioneering spirit of early innovators continues to light the way forward. Thank you for listening to the Computer Vault podcast. If you enjoyed the episode, please rate and review on whichever platform you're listening on, and be sure to keep an eye out for our next episode where I'll talk about a new topic. You can also check out my website at www.computervault.co.uk, where you'll find previous blog posts from the full and short podcast episodes and details of my computer collection, which includes books, manuals, CD-ROMs, floppy disks, magazines, cassette tapes, and some old retro computers too. If you'd also like to help support the podcast development, you can subscribe to us on Patreon at patreon.com/thecomputervault, where you can get access to new podcast episodes before they're released and exclusive member-only content. Thank you again for listening, and see you on the next episode.